Just a very brief welcome and introduction to this event. It's University Lecture, as we all know, is one of the most important times of the year. And it's when we celebrate our most creative minds. But it's also a time in which we celebrate the academic way of life. The people that we ask to come and speak are those whom we admire most because of what they've contributed to the development of knowledge. And I think I'd have to say that right now it seems more important to do this than at any time I can remember. On behalf of all of us, we're extremely grateful to Professor Gelman for giving us the chance both to honor him and to affirm the world of the university. And I now turn this over to John Coatsworth. John?
Thank you, President Bollinger, and welcome to this evening's University Lecture. This is a night we all look forward to, when disparate parts of the Columbia community have an opportunity to come together and to learn about the academic work of a distinguished faculty member whose current scholarship might otherwise remain outside our vision. I certainly count it as a privilege and a great pleasure to be surrounded by so many colleagues and students for this good purpose. Tonight, we will hear from Andrew Gelman, Higgins Professor of Statistics and Professor of Political Science. Professor Gelman is known to many of you for his public commentaries, making use of statistical methods to explain politics and polling. Tonight, his focus is different, but the subject is no less timely and compelling. The title of his talk is The Statistical Crisis in Science, How to Move Forward. Professor Gelman became a faculty member in Columbia's Department of Statistics 17 years ago, and then, 2 years later, in 2002, he received a joint appointment in the Department of Political Science. Before arriving here, he had received undergraduate degrees in mathematics and physics from MIT and had earned his master's and PhD degrees in statistics from Harvard. He is the founding director of Columbia's Applied Statistics Center and the author of a number of highly regarded books that have attracted readers in both academic circles and among the general public. His book, published in 2008, Red State, Blue State, Rich State, Poor State, Why Americans Vote the Way They Do, succeeded in upending political myths about partisan voting patterns and changed the way we think about elections and about American politics forever. Professor Gelman is something of an evangelist, actually an evangelist for improving the way in which we communicate scientific research findings to the public. He frequently speaks about the importance of making statistics visible and communicating them more effectively to the public, a subject that is also very much the focus of his admired classroom teaching. He has also maintained his own widely read blog for some 10 years now and is a contributor to the Washington Post political science blog called The Monkey Cage. That name, I should note, comes from a wonderfully resonant H.L. Mencken quote: "Democracy is the art of running the circus from the monkey cage." Professor Gelman's interests are wide-ranging. He has, at different times, focused his attention on police stops, social networks, public health, and redistricting. He has received some 24 academic awards, including the Outstanding Statistical Application Award from the American Statistical Association, the award for the best article published in the American Political Science Review, and the Council of Presidents of Statistical Societies Award for outstanding contributions by a person under the age of 40. As you know from listening to President Bollinger and from observing many of the most exciting new developments at Columbia, we are increasingly focused on bringing the university's vast knowledge to bear on the pressing problems of the day. Doing so has always been and always will be part of our mission. With that in mind, I want to conclude with a quotation from the speaker we honor tonight. According to Professor Gelman, quote, "Every field worth studying connects to one's everyday life. Statistics is not an isolated field. It connects to everything." I am sure that his talk will leave little doubt as to the rightness of that claim. Please join me in welcoming the 2017 University Lecturer, Professor Andrew Gelman.
Hi. So the other day, somebody sent me an email. They said, like, "Did you see this thing? It was in the newspaper about stents." So a stent is some sort of balloon that inflates your artery, and it said that stents do no better than placebo. But this guy said that wasn't true. He read the paper, and actually stents did better than placebo. So I was curious. So I read the article, and it was a randomized trial where 100 patients got the stents and 100 patients got the sham surgery, where they do the surgery and they don't put the stent in, which don't give me that look, because they consented to, be randomized. I think it's very safe. Like, there were no adverse events apparently, and they get, you get extra goodies. Like, if you participate in a medical study, they do nice things to you and they give extra care. So it seemed fair enough. And there was a difference. So the stent group did better than the placebo group, but not statistically significantly better. So they said that stents didn't work. It's kind of funny. I'm not an expert on the placebo effect. I think that's what, as a statistician, I'm not an expert on X, for any X that I happen to study. But I wonder about the placebo effect, because if there's a 50% chance you're actually getting the sham treatment, then I don't know if you get a 50% placebo or what. The people who did the study, it was a very professional job. They knew what they were doing, and they did standard good practice. So they asked people, which treatment do you think you got? And most people didn't know, and the ones who guessed right about 50%. So it seemed that people didn't know what they were getting. Anyway, I looked at the paper, and so I realized the analysis wasn't wrong, but they did this thing called a gain score, where they look at the improvement from pre-test to post-test. They didn't control for differences in pre-test between the groups. If you do that, you'll get more statistical efficiency. So I thought maybe I could get the raw data and analyze. Just kidding. But I was able to read the paper. You could actually deduce from the summary statistics in the paper what the analysis would be if you controlled appropriately for the pretest score. So I was able to reconstruct the analysis that they could have done. But before doing it, I got really excited, because I could tell from the differences between pre and post that when I reanalyzed it, it would make the effect bigger and the standard error smaller. And it was already at p equals 0.2, which isn't good enough. It's supposed to be 0.05, but I knew it would get better. So I had to go to work, teach a class or something. I don't remember. And so I quickly dashed off an email to my colleague at the New York Times saying, "Hey, this is going to be big. This is great." So then I went back, and I was figuring it out, and it did just what I said, except the p-value went from 0.2 to 0.09, which was not what it's supposed to do for the story, because it went to 0.04, and then I would be able to say, look, once you do the right analysis, it becomes statistically significant. So you can see that by doing the right analysis, it changes the story completely from stents don't work to stents work. The whole headline changes. Everything has changed. It's all, God, we did it, statistics. But, it went to 0.09. But then I realized this is even a better story, really, because what's so magic about 0.05 or whatever, right? I mean, so the real point is that, yeah, the stents did better, maybe. The difference, I don't care if it's statistically significant. The difference was not clinically large. And I think, actually, there's some issues. I think the study was very well done, but that's kind of the point, is I think there are some issues here, and I'll kind of get back to that. But first, I just want to say it's a pleasure to speak here. I've taught here for 21 years, and to have a room full of collaborators, students, family, and friends, it's really wonderful. It's a privilege to be at any university, but especially this one. And it's said that those of you who have taught know this, that the only way to truly learn a subject is to teach it. And I can assure you that my students understand statistics very well, because I know that because they've taught me so much. And I've learned so much from my collaborators as well. So let me tell you a story. This is something somebody sent to me in the mail a few years ago. I think they wanted me to make fun of it. Influence of Valentines Day and Halloween on birth timing, but I actually liked it. I'll show you the data here from the published article. They had the number of babies born every day for a 20-year period, and do you see that the heart there on the left? That's Valentine's Day. There were more babies born, and then fewer on the week before and the week after. And then, do you see, isn't that cute, the witch there? Yeah, that's Halloween. Yeah. So it's kind of funny because, like, not only are there more cesarean section births on Valentine's Day, because what shows love more than, but more natural births too, which seems kind of funny, like how could that be? Although those of you with statistics training will know that selection occurs even on the things that aren't selected, because the natural births are all the births that weren't induced or cesarean sections. So in fact, you get selection there too. Anyway, this is kind of interesting. It's statistically significant. You can see by those little stars. Someone sent me a paper the other day. It was some claim I didn't quite believe. I looked at it really carefully, and it said it was statistically significant at the 0.1 level, which you're not really supposed to say, but I just threw that out for those of you who are into jargon like that. If you look at this, it's like, is this real? You know, I'm not sure. What should you do? I think what we should do is look at all 366 days of the year. So someone made this graph for me. This is the benefits of collaboration. Is this hair trigger? Okay. Someone made this graph for me. You can ignore the curves. This is just the raw data, the total number of babies born each day of the year. You can see fewer babies on New Year's and July 4th and Christmas. There's Valentine's Day and Halloween, which sort of like, it's not completely clear, like, do they really stand out? You see a wiggling. There are about 52 of those cycles during the year, because it's not a 28-year period. So there's some confounding of day of week and date during the year. So we need to do a little bit more analysis. If we just look at this, it's hard to know what's going on with Valentine's Day and Halloween. God, this is so, okay. Someone made this graph for me, which I kind of like because I hate it so much. Because it's, there's a principle of statistical graphics that graphs are comparisons. And this graph is sort of a wonderful way of comparing what's happening on the 21st of every month, going across, which is kind of goofy. It also tells you more babies are born in the summer and the early fall, but you can see that much better from this graph. So this graph is kind of horrible, but I just wanted to convey that I thought it would be interesting to see that not everything we do is very helpful, actually. Okay, so I'll tell you the rest of that story once we have the data for you to see. Let me move on to the statistical crisis in science. I can start with an example. You might have heard of, someone did a study, they looked at 50 common food ingredients, and they scoured the medical literature, and they found of those 50 food ingredients, something like 40 had been discovered to either cause cancer or prevent cancer, some of them both. actually. Now, my point here is not that onions both cause and prevent cancer, but rather that there's a problem with how medical research is often conducted and communicated. And a problem also occurs in other fields such as psychology, medicine, and public health. And for example, the Stents story that I led off with has this issue. So a study is done, some data are collected, and then the result is this very strong conclusion. Like something works or it doesn't work. It's actually kind of funny if you think about it, because it doesn't matter how bad your data are, you always can say it works or it doesn't work. It's like a free headline. I mean, you could just be like, you could have a spinner and just generate random numbers, and that would be enough to get that. Not that anyone would do that, just generate random numbers. They might have people, but they might be measuring something that is so noisy that it's as bad as being random numbers. In particular, if you want to study things like what causes cancer in epidemiological studies, that's kind of noisy because people can get cancer from all sorts of reasons. So if you study a small effect, you'll be seeing the noise rather than the signal. Now, it's fine to see the noise rather than the signal if that's what you see. But the issue is if you misinterpret it and then go around telling people not to eat onions, that would be terrible. But I'll talk a little bit about political science rather than psychology and medicine, because political science, American politics, is what I study. So there have been some, we will hear about political science in a moment, but now it's time now it's time to return to the birthdays. So my colleague Aki Vetteri from Finland fit a statistical model to the birthday data. And it's a decomposition. So we start with the number of babies born every day between 1968 and 1988. Now, I'd just like to interject here that it's really great. Students love if you can have an example where you can find yourself in the data. You gather data from the students and then you plot them, which data point are mine? Well, a lot of you are in this data, right? So this is you can find yourself if you were born between 1968 and 1988. There are several components. There's a slow trend, a fast non-periodic component. You kind of need all of these. You need the slow trend because there was a time when having babies was less popular, then a time when having babies was more popular. You need a fast non-periodic component because there are just things that happen. People are in a good mood and they have more babies, then they're less in a good mood. There's fluctuation. We have day of week effect, fewer babies on the weekend, and the day of week effect changes over time. It became more pronounced as the number of scheduled births went up. And then you see a seasonal effect that there's a time, more well-known, more people born at the end of summer, early fall. And then finally, the day of year effect. Now this model was cool. We did not tell the model to look for New Year's Day, Valentine's Day, Leap Day, so forth. Our model had 366 parameters, one for each day, plus extra things for the 3 floating holidays, Labor Day, Thanksgiving, and Memorial Day. And it just sort of discovered from the data what was going on. And it picks up, it picks up. Valentine's Day is actually interesting because Valentine's Day is the only day that has too many babies. All the others have too few. Well, that's not quite true because December 24th and December 26th have too many babies. But that's because there's a sort of principle that the baby has to come out at some point or another. So if you have fewer babies one day, you have to have more nearby. But Valentine's Day is kind of special, so I actually really like that paper that found that. Then we got more data. This is from 2000 to 2015, and it's similar. I want you to go back and look at this one for a second. Do you see the scale on the y-axis here goes, I don't have control over this thing. Okay. Oh, I don't point at that. I point over there? No. Okay. If you look at what happened before, there's just a lag between when I click. Do I have to say it? Are you clicking for me here? What's going on with this? Because I click, it's like a delay. Okay. The effects are larger than, okay. This is what it was like before. And you see, I want to point down there, that's not so helpful. If you see that New Year's, they're about at 80 or so. Then if you look at the more recent data, the effects are larger. Could you click to the next slide, please? Thank you. Now they're around 60. So there's just a lot more induced bursts than there used to be. But I actually want to focus on something slightly different here. Look at what's going on around after 9/11, which is a less popular birthday now. Do you see that there's a 2-week period where there's too many babies? And that violates the baby has to come out somewhere principle. You can't be like scheduling your babies for 2 straight weeks. Like, where do those babies come from? Right? So what's really happening is that the sort of lump, the positive thing that's happening after 9/11 it's really not about scheduling birth. That's just a seasonal effect. Now look at that seasonal curve. Do you see how smooth it is? Now if we go back to the previous slide, yes. Now you see there's like a bump at the end of September. So there was kind of this model fit the data. The second model kind of fit the data well. I'm going to go back to the next slide now, please. Yes, this model sort of fits the data wrong because it puts in this slow change in September. It puts it on the bottom, and it should be really on the third thing. So we realized there's a problem with our model, and we have prior information that's not in the model. And the information is the baby has to come out somewhere, right? So our model said that every day, all 66 days of the year, there could be a spike, extra births or not enough births, and it tries to fit it. What we really need is a model with ringing. So it says, there's a day with not enough births, and then the days before and after have to have extra births to counterbalance that. Otherwise, it doesn't add up. So we didn't put that in the model. In their first data analysis, we got lucky, and it sort of worked out. But in the second data analysis, it didn't discover the right thing. And so there are a lot of points of this example, but maybe the most important is the way that we go back and forth between our model, our data, and our scientific questions. We're sort of circling through, looping back. And the stronger the model we make, the more we can learn when the model doesn't fit. Now, the other relevant point about this is it demonstrates a principle from mathematics, which is that if you can't solve a problem, embed it in a harder problem. This is a well-known principle of mathematics. If you can't prove a theorem about prime numbers, prove it on ideals, which is a generalization of prime numbers. If you can't sum an infinite series, then you solve the generating function. And instead of trying to understand what's happening 2 days out of the year, we're going to estimate what's happening in all 366. In statistics, this is called the blessing of dimensionality. Some journalists contacted us and they said, what about Friday the 13th? It's like, what about Friday? Well, this is just the 13th. You can do more with Fridays. Look at the 13th. Look at that. You see? It's kind of funny. It gives you a new insight into Valentine's Day. What's Valentine's Day? That's right. It's the 14th. So one reason Valentine's Day is so popular is that it's sitting next to the 13th. Now, that's not the only reason, because you don't see a peak the 14th of every month, but it doesn't hurt to be next to the 14th if you want to be getting extra births. The funny thing is, this pattern was in the data already. If I go back to the earlier graph, it's there. We just didn't notice it because we didn't know what to look. And you want to hear something really funny? Go back. We're going to go back to the ugly graph. Can you go back to the ugly graph, please? One more. One more. Yes, stop. Look at the 13th. Isn't that funny? I was like, oh, this graph is so stupid. It allows you to compare the same day of every month like I would really want to compare the... Actually, if I looked at this graph, spent a little bit less time laughing at it and more time looking, I would have seen, hey, what about the 13th? No kidding. It's right there all along. But, of course, you'll only see it if you look at it, right? Okay, the statistical crisis in science. So in political science, we've had published papers on, ovulation and voting. Did you know that during a certain time of the month, Sorry, sorry, Sophie's making symbols at me. I was distracted there. Did you know that during Did you know that during certain times of the month, women are 20 percentage points more likely to vote for Barack Obama? Actually, the published research said that married single women were 20 percentage points more likely to vote for Barack Obama, but married women were more likely to support Mitt Romney. Do you know that men with fat arms, college students with fat arms, were more likely to oppose economic redistribution? It was published in a research journal. Do you know that elections are determined by college football games and shark attacks? Again, this was all published. Now, these studies like these are kind of notorious in science now because they fail to replicate. Now, I won't say all of those studies failed to replicate. Some of them failed to replicate. Others, I'm pretty sure they wouldn't replicate if you were going to bother to redo them because the data are basically noise. The data in these studies are consistent with null effects. Or more to the point, they're consistent with effects that are highly variable, unpredictable, and context dependent. So I want to emphasize that I'm not going around saying that your hormones don't affect how you vote. I have no idea. I'm sure my hormones affect how I vote. I don't think they will change 20% of people's votes. I don't think they're going to change 2% of people's votes. I have good reason for thinking that. I think that the occasional person might be so pissed off that their college football team loses a game that they may vote a different way. I don't expect to see a systematic effect of that size. I'm not going to go around saying effects are zero, but I think effects are highly variable. Now, I'm going to get back to the sort of political point of studies like that, but I want to emphasize that these problems aren't just with like joke studies like ovulation in voting or fat arms or whatever. They're also in serious research. So for example, there was a study done about 25 years ago that was recently published. It was a study on an intervention for 4-year-old children in Jamaica. They had 130 kids, and half of the kids got a certain an educational intervention with their mothers at the age of 4, and half of them didn't. Now, it only got published recently because they followed them up for 20 years, and they recorded their earnings once they were grown-ups. And they found that the kids who had the intervention had 42% higher earnings than the kids without the intervention. Now, 42% is pretty good. In fact, not only was it a large number, but it was statistically significant. To be statistically significant, you have to be at least 2 standard errors away from 0. A standard error is a measure of uncertainty. And so the standard error of this study was about 20 points. So what that means is, what does that mean? Well, that means that they couldn't have seen an estimate of less than 40%, or it wouldn't have been statistically significant and it wouldn't have been published. So here's 0. If this is 0, and this is 1 standard error, which is 20% effect, any effect estimate had to be at least plus 40 or minus 40, or it wouldn't have been published. So when they said it was not only statistically significant, it was also large, it was statistically significant, it had to be large. Now let's just suppose, well, I'll say this study had some various data issues, which I'm not going to go into here. Like some of the kids left Jamaica. The kids who left Jamaica actually had higher earnings than the ones who didn't leave Jamaica. More kids in the treatment group left Jamaica than in the control group. There were different missing data. That's okay. That always happens. Let me ask you this: what if the true effect was 5%? That would be pretty good. If you could do an intervention for 4-year-olds and then 20 years later their incomes are 5% higher, that would be great. Well, if the estimate were 5%, then the published estimate from this study has to be at least 8 times larger than the true effect. Well, then you might say, well, 8 times, that's kind of too bad, but at least they got the direction right. But I don't know that they got the direction right. What if the true effect was minus 5%? Oh, that's silly. How could it hurt to do an intervention? Well, you could imagine, oh, they thought, well, we're all set. We don't need to do X, Y, and Z because we're getting the intervention, whatever. I don't know. Maybe it hurts. Because after all, if they spent an hour a week or 2 hour a week doing this, maybe they were doing that instead of doing something, more useful, right? With their time. Opportunity cost, right? We've heard about that. What if the true effect were minus 5%? Well, the estimated effect would still have to be at least 40%. So it could be too high by a factor of 8 in the wrong direction, even. Now, we call this the statistical significance filter. It leads to systematic overestimates of effect sizes. It's one of these things that everybody knows and people don't know. So they call these things unbiased estimates, even though they can be 8 times higher than the true effect. But it's a little bit worse than this because there's a feedback loop. And the feedback loop goes as follows. I'm designing a new study. So how large should my study be? Well, I have to have a sense of how large could the effect be. So I look in the literature, and the literature says, oh, this treatment has an effect of 40%. Oh, this is a pretty big effect. I guess if my study is this big, I'm very likely, I have a high power. I'm very likely to discover something in the future. So then someone designs their new study, being completely sure that their new study is almost definitely going to succeed because they think they're looking for this big effect. Then they do the new study, and the data look kind of noisy, and they manage to find something statistically significant. But of course they do, because they knew ahead of time the study was going to work, right? So you get into this loop. It's the winner's curse, they say in economics, right? You win the auction, and by winning, you lose. Well, I want to write a paper sometime called Death of a Paradigm. And in this case, the paradigm is a statistical paradigm in which you come up with an idea, you study it, you do an experiment, you test it, you find out it's statistically significant, and you publish the result, and that affects policy. And the trouble is there are not so many low-hanging fruit around anymore. They've been plucked already. Indeed, in medical research, it's considered unethical to estimate large effects, usually. Because in medical research, you're supposed to compare to the best available alternative. The only reason they could compare stents to placebo was because they had a sense that maybe stents weren't particularly effective. So we're actually always studying small effects. We're studying small effects, but we're using a statistical approach that's designed to study large effects, and it's not working. Now, at this point, I think the natural attitude of the statistician would be to say, well, obviously people should take more statistics classes. Maybe statistics should be a requirement for more undergraduate majors. Maybe we need more faculty lines. Here I have the president of the university here. I can really make the case for that. However, actually though, I think that scientists have been listening to us all too well. They've been listening to our message, and our message is that you can use statistics to extract signal from noise, that you can win repeatedly. Even my own statistics books have this flavor, which is, here's a problem, here's some data, here's the result, I have a 95% confidence interval, exclude 0, I've learned something. Another win for statistics, over and over again. That's the message that we sell. We are telling people what they want to hear. I had this article, the colleague called the AAA tranche of subprime science. And the idea was that, just as with the AAA the mortgage bonds, that there's all these data, and researchers scoop out the statistically significant results that float up, and then they collect them, and they put them together into statistically significant meta-analyses, and it's all just kind of froth, but they get things that are like the AAA bond, which is P equals 0.00005, and then that's supposed to be really valuable, but it's really not necessarily so valuable. Now, for decades, for nearly a century, statisticians have been patiently training the world, people, on how we can extract signal from noise. Like polling, right? Hundreds of millions of voters, and yet a survey of 1,500 people can tell you about them. It's counterintuitive, right? That you can learn about the effectiveness of a treatment from a randomized experiment on 20 people. Yes, under controlled conditions, this works. Casinos really do make money. The theorems are not false. But the theorems are only as good as their assumptions. How would it work if you ran a casino and the probabilities on the dice varied based on whether the dice were hot or cold, or who was throwing the dice, or whether the person sitting next to the dice thrower was making a face at the person throwing the dice, or whether people knew that they were supposed to get high numbers or low numbers, or if there are any other information leakage. All of a sudden, your casino might make money, it might lose money, but the modeling would have to be a lot more difficult. So I think we have to recognize that we statisticians have been selling statistics as a form of uncertainty laundering, and maybe we shouldn't be doing that. So what then to do? Well, remember the lesson from the birthday problem, which is when a problem gets too large, embed it in a larger problem. When it becomes too difficult, embed it in a larger problem. So here's an example from one of our collaborative research projects. This was a survey that I did with some colleagues at Microsoft Research using the Xbox video game platform. This was done in September and October and November of 2012. You had the ability to click and vote, and 300,000 people did so. Here were the data. You can see from the graph that in September, Obama and Romney were very close. The number of people with no opinion went down. Romney took an early lead and kept going, and at the end we ended up with President Romney, and I'm sure we can all agree that that wouldn't be the worst possible outcome. That's not what happened, though. Something went wrong. It's almost as if people who play the Xbox aren't a representative sample of voters. We can compare. They actually fit with ethnicity pretty well. Xbox players have they're more young people play the Xbox. And there are some other differences. Xbox players are slightly more Republican, less Democratic, which is why Mitt Romney was winning among the Xbox players. So, well, it turns out, I don't want to spend too much time on the example, but I'll tell you one thing, that although the data are not so great, not representative, we can adjust them and learn a lot. And one reason is because whether you play the Xbox, you're not selecting on people's political attitudes. I wouldn't use an Xbox survey to answer questions like, what video game platform do you play, for example. And I wouldn't use a survey on Fox News to estimate people's political attitudes. But this kind of worked. So I showed this slide only because it's like, why are we doing polling on the Xbox? Well, let's be honest, it was a publicity stunt for Microsoft, okay? But it's not like conventional polling is so great. Conventional polling is falling apart. Non-response rates are over 90%. As if current trends continue, non-response rates will soon be in the hundreds. So it's like, well, you can't stand still, right? Okay, so we adjusted the Xbox poll for demographics. We shifted based on their ethnicity and their age and so forth. And then you get this estimate over time where Obama was ahead, then Romney was ahead, and then Obama won. This is very close to what you would get from something like pollster.com. Although it's kind of impressive because each dot is data from a separate day. This is not a running average. It's actually the data. Pretty cool. We did do better, though, because in this poll, we also asked people, are they a Democrat, Republican, or an independent? And we asked how they voted in the previous election. And we can also adjust for that because the poll had too many Republicans. And after you do that, you get the dark line here. So the light line is what you got from just adjusting for demographics. So by adjusting for partisanship, that actually gets rid of more than half of the variation over time. What this tells us, I mean, we went through a lot to try to interpret this, but I think what this tells us is that most of the variation in the polls is due to differential non-response. So when your candidate is not doing well, you don't really want to respond to the poll. And so your candidate does even less well in the poll. And when your candidate's doing well, they're like, yeah, I'll play the polling game. This is fun. Yeah, how's my guy doing? Let's check. Let's check again. Let's see, is my guy still ahead? This is great. This is fun. And so this exaggerates swings in true public opinion. Now, what's going on here is that 60% of people vote, but less than 10% of people participate in polls. So answering a survey is optional. And whether you answer a survey depends a lot on your mood. So this is kind of an amazing example because not only did we do better than conventional polls, but we learned something new. And it all kind of fits together. And again, as with the birthday example, it fits together because we're looking at more things. If I had just studied one day and tried to adjust it perfectly, I wouldn't have learned. We wouldn't have learned from that. This is just from 2016. This is a graph where each dot was a poll. Alan Abramowitz, a political scientist, sent this to me. Each dot is a poll, and he's plotting the percent support, the margin in favor of Hillary Clinton in the poll versus the percent of people who were said that they were Democrats in the survey. And it's like, look at this perfect correlation. On surveys with more Democrats, Hillary did better. So it's still happening. Okay, now where does this lead us? We're in a world of big data. Okay, big data are typically convenient samples, not random samples. They're observational comparisons, not controlled experiments. They're available data. They're not measurements designed for a particular study. So as a result, when analyzing big data like the Xbox poll or modern public health data, we need to adjust. We need to extrapolate from sample to population. We need to match the treatment group to the control group because it's not a randomized experiment. We need to generalize from observations to underlying constructs of interest. But big data need big model. Nowadays, I spend a lot of time with my colleagues, some of whom are in this room, working on STAN, which is our computer program that fits Bayesian models. It's named after Stanislav Ulam, who was a 20th century physicist who with his colleagues developed the so-called Monte Carlo method for solving math problems using random simulation. And it's like we have this big computer program that fits big models. The most important aspect of a statistical method is not what it does with the data, but what data it uses. And so the important part of a big model is that it's big enough to allow you to put the data in. This afternoon, my department chair, Richard Davis, came by. He said, "You're giving this talk." He said, don't forget to plug statistics and say how important. So I was thinking about that. So math, I'll talk about math, but like mathematics plays 3 roles in this story. The first is it's a substitute for replication. It's a substitute for data. Someone does a study, and I can say, looking at the math, don't bother replicating this study. It's not going to work. It's all noise. I can see, your effect is no more than this big, and your standard error is this big. So math helped me. Math is a substitute for data. That's probably the most important role in statistics. Second, we use mathematical models for variation. How we did stuff like that birthday example or the Xbox, we have models. You can't just stare at the data and do that. Finally, we need a lot of math to make the computing work. So to actually fit the models we want to fit require a lot of research. There's 2 things I wanted to mention before closing. And one is the folk theorem of statistical computing, which is that when you have a problem with your computation, typically there's a problem with your model. When your computer is running slow, there's often like something that went wrong, that you did wrong. And that again, like I'm sort of mentioning that like a little bit of what it feels like to do what we do. The other thing that I wanted to say was that about these political studies, claims that voters are affected by little things, strange things like sporting events and shark attacks. A claim that voters are shallow is very popular on the left and on the right. And on the left, you can say, well, voters are so shallow, the system is a sham. On the right, it can be used to discredit democracy and say, well, gee, if we don't trust voters, we should diminish the political sphere, get rid of taxes, because we don't trust democracy. And I don't think that's right. And I say that kind of as a statistician. I think a lot of these claims that have been made based on very noisy data. People have set themselves up to find effects. So they look to find something and they find it. And in that world, every nudge has a large effect. And I don't think does not seem to actually describe the world as I see it. And that Xbox example showed how all these swings that you see in raw data, when you look at them carefully, there's actually a lot more stability. So in summary, I want to close with these words here. That's all.
Thank you, Andrew, for a brilliant talk and an entertaining one as well. The floor is open to questions. There are microphones in the aisles. If you would step there and just identify yourself and then shoot your question to Andrew. And I should say before we begin that there is a reception in Andrew Gelman's honor that will be taking place in the faculty room, which is just behind the stage here. So you are all invited. Here.
Hello, thank you. My name is Flynn Schuyler. I'm a biomedical engineering student. And I was very interested in what you said about the stent and placebo study and how you reconstructed the data to obtain a different p-value from the results. And so my question is, since so much of medical research is based on this idea of drug versus placebo and before and after effects, why is there not a standard for medical research so that given a certain set of data, all researchers would obtain the same p-value?
I don't think the p-value is so important. So I think we should be moving toward a framework of continuous quality improvement, which is an idea that's been around in industry since the 1920s, has been very popular in the Japanese auto industry for many decades. I think the model, medical research, I think the model should not be, we have this isolated thing which works. I think we should be talking about continuing to process improvement in which I believe that the doctors and patients who are trying out these methods should be more active participants. And so the point is that a stent is not an abstract thing. People are doing it for a reason. And I think that there should be, in the ideal world, more experimentation and data collection at the level of the individual patient, moving away from this sort of, Fordian idea of there being a single thing that's done for everybody. In that case, the p-value is kind of irrelevant.
Thank you.
Yes, over here.
Dr. Gelman, thank you so much for a wonderful talk. I'm a medical student, and as someone transitioning to residency next year, your stent problem was well received. I wanted to ask you, how do we fix polling? Obviously, a tough question, but I want to get your thoughts on it. There's a well-known event that happened about a year ago where we got things wrong, and Virginia was, I think, another interesting example where the polls were off.
Oh, how do we fix polling? Well, you wouldn't want polling to be too good, right? I mean, in the sense that voters do get to change their mind before the election. The 2016, the national polls were pretty good. There were certain state polls that didn't do so well because they didn't do enough adjustment. They weren't all adjusting for people living in, for education or urban, rural. It's a funny thing about state polls, that a state poll is as expensive as a national poll, because surveying 1,500 people just costs the same amount. But the people who do state polls, there's a lot less money to be made in a state poll because the market is smaller. So what do I think is a solution? I think the solution is to use the national polls and use partial pooling, Mr. P, to estimate state-level opinion from the national polls.
Over here.
Hi, my name is Amir. I really enjoyed your talk. It's a very related question, but near the end of your talk, you mentioned about voluntary response bias, and especially things with like an Xbox poll. And on campus, you know, there are these polls all the time. When someone is designing these type of polls or surveys, what should they have in mind from the outset to try to eliminate that bias before they have to take into account all those variables?
I think the number one thing is you should think of the people who respond to the polls as your research partners. Don't think of them as like animals that you're measuring. Like think of them as like participants. So figure out like what you want to know from them and how you can ask it and how they can help. Because conditional on someone responding to a poll in the first place, they probably want to help you. I mean, one reason why people so I think you want to take advantage of that resource, and that's tended to be wasted. Traditionally, what people do is they do a poll and they're like, hey, we tricked somebody into answering our survey, now let's bombard them with a bunch of questions. But I think especially in a particular area, like not like an election poll, but something you're personally working on, you can get a lot out of showing some respect for your survey participants.
Thank you.
Over here.
Hi, Professor. So you linked in your blog a paper that questioned the validity of confidence intervals and standard errors. And in that paper, they pointedly say that we shouldn't try to interpret standard errors because that's like to draw inference from statistics, because that's essentially applying a Bayesian framework. So without getting too technical, when we read papers, should we be assuming that the standard errors are close enough to what the Bayesian alternative would be, or should we take these with more grains of salt?
Well, I usually would interpret the results as inferences based on certain conventional assumptions. So the conventional assumption, like if we take the Jamaica study, the early childhood intervention, the conventional assumption is the effect could be anywhere from like -infinity to +infinity. And in that, if it could be anywhere in that range, this is what you can learn. If you then say, well, actually, realistically, I think the effect is probably less than 10%, then that will change the interpretation of these statements. So in some sense, the problem is not with the standard error, it's what people do with the standard error.
Okay, thank you.
Hi, my name is Charles. I'm a PhD student in the statistics department. And I want to pick up on something you said at the beginning of your talk, which was my specialty is X and there's no such X. And it seems that in light of the statistical crisis, the reaction has been, well, scientists need to learn more statistics. They need to be more familiar with the method. And I'm wondering, well, how much does it go the other way? How much do statisticians need to learn more science? And has there been initiatives in that direction?
Well, I typically feel that every statistician is an expert in at most one subject. So I really am an expert on American politics. I know something about that. But like everything else, like toxicology or the other things I'm working on, I'm kind of winging it. But there aren't that many statisticians. There's a lot more of other people. So even if every statistician, I think it is good for every statistician to be an expert in some area, but that's somehow kind of not enough. But again, like I think the original sin in statistics was this idea that we can get strong conclusions from any data, and and we have to avoid that. So we have to, as statisticians, I think we have to stop doing that to people before worrying about what to do next.
Thank you.
Hi, very much thank you for this last quote, because I think it's very meditative somehow. So I wonder, why do we need to reduce the variation? But especially in statistics, you want to have the variation data for you to reveal the relations, to show the result, the relations. But then why don't you want the variations? And use that. I think something you can apply to that for your state of mind is that, I want to hear what you say.
You have to sort of separate yourself from the data, okay? So data have variation. There's variation in the data. We do this study and the Stents, and we measure how long people can exercise, and it's a noisy measure. But I think that probably what you really want to be doing is getting better measurements. Doing comparisons within people, like getting multiple measurements. Like in the Xbox survey, people responded multiple times. So we could have information on people changing their opinion. And I think a lot of, researchers are trapped in the data. And one thing, remember I told you about this feedback loop where people overestimate the effect size, it gives them overconfidence, then they do the next study. Well, another problem of that is it's kind of, when it's too easy to win like that, there's not much of a motivation to work hard and get good data. And anything, you're doing a study, what's the ultimate effect, whether people live or die? Okay, well that's great, but a lot of things cause people to live or die, so your data are going to be very noisy. You probably want to get some intermediate measurements. And I think there's kind of a negative message and a positive message that I have. And the negative message is that it can be sort of too easy to fool yourself, and even worse, to fool other people with noisy data. So the idea of the negative message is, no, I don't want to do that because I don't want to do bad science. I want to discover real things, not fake things. Or I don't want to publish stuff like that. I don't want to do stuff like that because in the future it's going to get rejected by a journal because it's not pre-registered. Whatever it is. Then there's a motivation to stop doing that. But then how do you do things right? Then you have these examples where we fit big models to the big data. But you shouldn't think of the data as just sitting there being noisy. It's your job to get non-noisy data, or to measure what you want to measure, or to try to do that.
So one more question, do you meditate?
What?
You meditate?
Oh no, this is is
Okay.
the Serenity Prayer associated with Alcoholics Anonymous, and I just altered it slightly because
Because it
it
aligns with-
it struck me that this idea that the variation, I think that it just seemed like it was perfect, so that's why I
It is. Thank
did
you.
that slight alteration.
Andrew, you are now my model for someone who can keep us cool in the face of recalcitrant technology. Thank you for a brilliant lecture. Thank you for an entertaining lecture, and thank you for dealing with the PowerPoint that didn't
Can I just,
cooperate.
before you say goodbye, I
Please
want to
do.
tell you tell a story, because probably the best talk I ever gave was when I was speaking at MIT, and I was giving a talk on statistical graphics, and the power went out, and it was on graphics. And so we were just talking. We had a whole conversation about graphics without using any graphs, and it was great. So yeah, you don't need the technology. You can't rely on it.
Thank you very much. You're all invited to a reception.